Alright, let us go over section 4.1, anti-differentiation in this video. This one's a little bit longer, so I'm probably going to stop after going over the first learning objective. I'll go over evaluating indefinite integrals using basic rules of anti-differentiation, and then I will come back and start from initial conditions. This one will be a little bit shorter. But I got about 7 examples in total in this video. Let me go over the first 4 with you, okay? All right, so today we are starting that second big branch of calculus. The first 3 chapters in the first 13 weeks of our Math 261 class, we were going over differential calculus. We were taking derivatives. Starting now for the next 2 or 3 weeks. We're going to be going in reverse. We're going to take antiderivatives. We're going to find something called integrals, okay? So just going backward, and the second calculus class is where you're going to do more of this integral calculus. So if you're taking Calc 2 next semester, you will continue, and I think we stop right before integration by parts in 261. But we will go over integration by substitution in our class, and that's the last topic that we will go over. I want to go over a couple application problems, but I'm going to talk about your exam 3 that's coming up. All right, let me write down. So today, this is week 14 right now. Week 14. This week we're going to go over 3.9. We did related rates, 4.1 and 4.2 this week. Okay, so it's this week. Whoopsie, too many E's. Week 15, we're going over 4.3 and 4.4, and that's where I'm going to stop for exam 3. Exam 3 will cover on April 30th that I have planned. We'll cover everything from 3.6, marginals and differentials, all the way up to 4.4, okay? I will have about 1 class to go over 4.5, integration by substitution, and 5.1 and 5.2. Just want to look at a couple application problems with you before the final exam. But with us losing a couple days with everything changing, we're going to be covering about 3 sections. But we did that last week. Week 13, we went over 3 sections, and you did a great job on it. So I think we can do it. So I'm going to go ahead and do about half of this section, 4.1 today with you. And I will come back and do the second half, the initial points problem, initial conditions problems on Thursday, okay? Alrighty, so it's very important you let me know. Email me if you are not available on April 30th from... I'm trying to give the exam on the same time our class meets. 9:30 a.m. to about 11 a.m. If you're not available to take your exam 3 next Thursday. Is that next Thursday? That's gotta be Thursday because we won't have... Okay, where are we? Next Thursday is... yes, it's next Thursday. All right, so next Thursday, if you're not available, I need to know about it very soon so that we can schedule something else. And for those of you who already did that, thank you so much. So let's start chapter 4, section 4.1, anti-differentiation. And we're going to be looking at indefinite integral in this lesson. And 4.2, we're going to do antiderivative as areas, and we'll do that on Thursday. But first, what is anti-differentiation? Now, remember when in your Algebra 1 class, your teacher told you to first FOIL x plus 2 times x minus 5, right? And then you guys FOILed it. You got x squared minus 3x minus 10, and you're happy you got it. But then, all of a sudden, she's like, guys, let's factor, and ask you to go backward. And factoring is when a lot of people kind of lose it, really. But that's what we're doing now. We work with one direction. We worked on taking derivative, finding the derivative, differentiation, all these skills for the first 13 weeks of our class, right? And now I'm going to ask you to go backward. So the antidifferentiation is the process of differentiation performed in reverse. So we're going to go backward. And just because we're so good at it now, we're so good at taking derivative, we even know how to take do implicit differentiation. Some of them, like without even us going over the rules, we can find the antiderivative without even discussing some of these rules, okay? And we'll do that for the first couple examples. Now, take a look at this with me. If the derivative of big f of x is equal to little f of x, then let's give some examples. Say that the little f of x is 2x. I should probably say the other one first. If big f of x is x squared, big f of x is x squared. Let me write that. What is the derivative of this big f of x, x squared? What's the derivative of x squared? That is 2x, right? So we were going this direction so far. I was giving you, hey, here's x squared, take the derivative, and you gave me 2x. What we're going to do now is we're going to go backward. I'm going to give you 2x, and I will ask you to find the antiderivative. In other words, what's that original function if you take the derivative that you will get 2x? And here's the thing, though. Notice how I said 2x is an antiderivative. I'm sorry. X squared is an antiderivative. It's not the antiderivative. Because here's the thing. Consider another function. Consider another function that says x squared plus 5. X squared plus 5. Take the derivative of that. What is the derivative of x squared plus 5? X squared will give me 2x, and derivative of 5 just turns into 0, right? So guess what? This big f of x also has a derivative of 2x. What about the other one? The third one I give you is x squared minus 17. What is the derivative of x squared minus 17? Well, that is also 2x because derivative of subtracting 17 is just 0, right? So here's what we notice. These antiderivatives are not unique, right? Because we can have multiple different functions who can have the same derivative of 2x. So when you guys are taking this indefinite integral, we'll read about it a little more. It's very important to know that there is, if you have a constant in your original function, the derivative will just, it can have multiple different constants. So like, for example, here the constant was 5, right? Here the constant was negative 17, and it didn't matter what I had added or being subtracted to this x squared term, because those just turned into 0. So when you find the antiderivative, let me go ahead and talk about this theorem that this leads us to. The antiderivative of little f of x is the set of functions, big f of x plus c, and that c can be plus 5, can be negative 17, that c can be any constant, such that the derivative of this big f of x plus c give you the little f of x. And this plus c that we're going to make sure to put on every one of these indefinite integrals are called constant of integration. Okay, constant of integration. So, maybe I'll show you something like, well, I can't really ask you to do an example yet before I introduce you the symbols yet. So let's go ahead and talk about the symbols now. How do we write this? Because if you look at the way that we were writing, it's really about, if you read it from left to right, we were going from the derivative of f of x is little f of x, right? But I want to give you a way where we can say the other way around. And that one, you've probably seen the symbol. Draw this integral symbol and say little f of x, and make sure to write dx equals big f of x plus the constant of integration c. So write this notation down for me, and we'll talk about what this notation is on this page, okay? So this equation is read as the antiderivative, the antiderivative of little f of x with respect to x. Now, the part that I'm highlighting, guys, with respect to x is from this dx, is big F of x plus c. So we can read this as the antiderivative, or we can say the other way of saying it is the integral of little f of x. And the part about this with respect to x is that dx part is big F of x plus c. So two ways to read it. We can call it the antiderivative, or we can call it the integral. And I think I tend to say both ways. All right. So the expression on the left side is called an integral. Hold on, I'm giving my dog some doggy bones right now. All right, go away. The expression on the left side is called an integral. Whoopsie, not with the highlighter. Integral. And I think I should be a little more careful over here. Let me go ahead and add one more description in front of this integral. Call this for me, please. Indefinite integral. Now, for right now, we don't have any things, like, take a look. What we're going to have later is we're going to have like a number in the bottom and number on top telling us to go from what number to what number. If you have that, we're going to call them definite integral. But for right now, we don't have any of those right now. So if you just have that symbol, that's going to be indefinite integral. And that symbol is the integral symbol. Is the integral. And f of x is the integrand. Like, you know how you have something in here like 3x inside and 3x in there, we called it radicand, right? So f of x, what we have inside, we call that integrand. Okay, all right, so just going over what these are. Okay, now last one, the symbol dx, and we want to make sure we put that to tell whoever's solving our problem what they are taking this integral what variable respect to. So the dx can be regarded as indicating that x is the variable of integration. Let's write it that way. Is the variable of integration or integral. Similar to how we use ddx to indicate that the expression follows, it is to be differentiated by with respect to x. Like we have d dt, then we were differentiating with respect to t. So make sure you write that, because maybe later in Calc 2, you'll be taking multiple integrals, and it's important which variable that you are using to do this integrals. So all right, so that's really it for how to read and what it is, but let's actually do them. Let's actually find some indefinite integrals and find these antiderivatives. Okay, so first for I'm not going to give you any rules yet. We're just going to go ahead and do this by knowing that antidifferentiation is just the reverse of finding the derivative. So here's a question. What kind of function has 8 as the derivative? And you know, 8x does, right? But it's not just 8x, but also anything else that has 8x, like, for example, like if you have 8x plus 7, if you take the derivative of 8x plus 7, what's that going to be? That's going to be 8, right? Because the 7 really doesn't matter. What about 8x minus 105? If you take the derivative of that, that's just going to be 8, right? So that plus c that I'm going to ask you to keep on putting for these indefinite integrals, I need you to really put it. That constant of integration is necessary, okay? So because it's not just going to be 8x, it can be anything else in the family of this 8x. And we can check this. You can check by really finding the derivative of 8x plus c. What's that going to be? That is simply 8, right? So that's what it is. We're finding the original function that would give us the derivative of the integrand. All right, let's try another one. What kind of function has the derivative of 3x squared? what if that function is x to the third power? Let's check that. Check. What is the derivative of x to the third power plus any constant c? Which we know that constant c is just going to give us 0. So if you take the derivative of x to the third power, that's going to be 3x squared, and that matches, right? Don't forget to put that c. And just by thinking about this reverse process, we can actually find a couple of these antiderivatives. All right, next one. It's a harder one. But you remember what kind of function has a derivative of e to the x? Well, you do know is e to the x. But remember, it can be e to the x plus any constant, plus or minus any constant. So if you insist to write this check, which is kind of just silly, what is the derivative of e to the x plus c? And the answer is e to the x. So ta-da. Yeah, I kind of want to give you the rules now, but maybe the last one, this one. I do want you to write it down very carefully, though, because here's the thing. You do know that the derivative of natural log of x is equal to what? 1 over x, right? So, but here's the thing, though. Hold on. Let me go ahead and... Because you know what I want to add over here? I do want to put plus c. If you take the derivative of natural log of x plus any constant c, that's going to give you 1 over x. And we learned that in previous chapter. But, it's not going to be too nice for you to say this equals natural log of x. In fact, you're going to have to say natural log of absolute value of x plus c. And, you know, it's just... Why do we have to include this absolute value of x? And the reason is, I mean, if you take a look at this guy right here, what is the domain of this 1 over x? We do know that x simply cannot be equal to 0, right? But it can be positive, it can be negative. But if you look at the domain of this, oh my goodness, domain of natural log of x, it's really what? Everything greater than 0, right? Now, the domain doesn't exactly match, right? Because the integrand had a domain of x cannot be equal to 0. But if I write this as just natural log of x, then the domain is really everything greater than 0. And I'm ignoring the values that are less than 0. But what if I write it as absolute value of x? Then the domain will be everything. Then the domain will be everything greater than 0 and or everything less than 0. In other words, simply x cannot be equal to 0. Now, I think I don't know, I'm thinking. I may ask you to prove or show or explain why is the antiderivative of 1 over x dx is natural log of absolute value of x instead of just absolute value of x plus c. I might put that on your exam and see if you can explain that to me. But there are a lot of things, videos and text that you can read about this. But just wanted to kind of give this to you. Make sure that when you are finding the antiderivative of 1 over x, and it's just because of because we want to keep the same domain, make sure you write that it is natural log of absolute value of x, not just natural log of x. And don't forget about the c, okay? And we can spend about 10 minutes talking about why this notation with the absolute value is better. But I may do that in another video. But I don't think I should ask you to do that on your exam. But just remember that, because I think I see a couple homework problem that's asking you to differentiate. Find the antiderivative of 1 over x. In that case, you need to include that absolute value bars around your x, okay? Alrighty, now, that was enough of guess and check. Why don't we talk about some rules of antiderivative so we can apply these rules? And the rules, I'm going to go up to number 4 in this video. The constant rule we kind of already looked at. Remember, if you had integral of 8 dx, then that just turned out to be what? 8x plus c, right? So if you have any constant, say, call that constant k. And we're finding the antiderivative with respect to x. And then that's going to be k times x plus some constant c. So that's the rule for constant. But the power rule, I will highlight this one because this is going to be very important, okay? We're going to be using this very often. But this power rule, look at this for me. It applies when n is not less than 1. It applies for every other number, but it doesn't work for -1. And we'll see why, okay? And it's actually this case right here. But what does n stand for anyways? N is the power, n is the exponent. And what we're going to do is this. You know what? Let's talk about this A2 power rule and go over some examples. And then we'll come back and talk about A3 and A4. Power rule is so important for this antiderivatives. I did write this down right here. Step number 1. Increase the exponent by 1. So increase the original exponent by 1. And then what you're going to do is you're going to divide that term by the new power. Okay, let me do an example on this very page and then I'll go to the next page. What if you're asked to find x to the 8th power? What if you're asked to find the antiderivative of x to the 8th power dx? Well, increase the exponent by 1. What's that going to be? X to the what power? 9th power. And then you're going to divide this by the new power of 9. That's what they're saying. What if you had x to the, let's say, I don't know, I can't be too creative, 105 dx. Then that's going to be x to the what power? Increase the exponent by 1, so 106, right? And then don't forget to divide this by the new power of 106. This is what it is, really. That is the power rule for antiderivative, and you can solve basically almost all the problems on your 4.1 homework using this power rule. All right, let's apply this power rule on example 2. Okay, now some of these powers needs to be rewritten, I agree. But let me start with A. I'm just going to make some room for my A. And this one's ready to be just completed. We got this. Now increase the power, increase the exponent by 1. So that's going to go up to what? X to the 8th power, right? And then what do? You divide by that new power. So the answer is x to the 8th power over 1. I guess you can write this as 1 over 8 times x to the 8th power. And what would you do if you just want to really see? Find the derivative of 1 over 8 times x to the 8th power with respect to x. And that's going to give you what? 1 over 8 times 8 times x to the 7th power, which is going to be 1 over x to the 7. And that is the same thing as the original integrand. So this is how you can check it. This is the check. You don't have to check it. You can check it mentally, but just wanted to show you one. All right, let's take a look at the second one. Well, the second one, you know, it's not, the exponent is not really written out. So what I'm going to do is this. I'm going to go ahead and rewrite this as integral of x to the what power? 1/2 power dx. Now, let's apply the power rule here. If you apply the power rule, you go up by 1. You go up by 1. So if you do 1/2 plus 1, that's going to be 3/2, right? So the new exponent, the new power will be 3 over 2. Now remember, we divide by that new power of 3 over 2, right? So it's a little messy, but remember, when we are dividing by a fraction, it's going to be the same thing as multiplying by its reciprocal. So I can simplify this. I can rewrite this as 2 over 3 times x to the 3 over 2nd power, okay? So, I mean, both are fine, but you see how the right side looks a little bit prettier. Now, but I'm making a very bad mistake. I don't know if you caught it. Now, I've been ignoring, I've been being so bad recently. Look, what did I forget? I forgot about my constant of integrations, okay? So what I want you to do is go back to your notes and just stick that plus c everywhere for me. I forgot about these plus c's. Plus c and plus c. I'm so glad I found it right now. All right, give me 1 second because I was going to finish the entire notes without my plus c. You need that plus c. Okay? And then I would even put it in here too. Plus c. Okay. Now that's good. Now I can go on. All right, let's do the very last one. Let's do the very last one using that power rule. This time I have 1 over x to the third power. Rewrite this first, right? Rewrite this as x to the negative third power. And then we're going to apply that power rule. So, go up by 1. Okay, if you go up by 1, the new power will be negative 2. And divide by that new power of negative 2. And don't forget about what? Oh, don't forget about your constant of integration, plus c. Please put that plus c. We sometimes forget, but we don't want to forget. All right. So, I mean, that is it. If you want to rewrite it, I guess we can rewrite it as what? Negative 1 over 2 times x squared plus c. But we found it. If you want to check, you can take the derivative of our answer and see if it gives back 1 over x to the third power, okay? All right, so we use what rule? The power rule to find antiderivatives here. This power rule is amazing. This is great, but it doesn't apply for every number, okay? Almost all real numbers, but take a look. Power rule for antiderivative is valid for all real numbers n except for n equals negative 1. I mean, why not? Let's take a look. Let's take a look. What if you have x to the negative first as the integrand? And let's try to apply this power rule. What do? You go up by 1, right? You go up from negative 1 and up. So what's the new exponent? The new power is 0. And then you're going to try to divide by the new power of 0. And then if you even try to put c there. But here's the thing. What is this mess? Can you divide by 0 in math? No. So that's why if the exponent is 0, this rule does not apply. Unfortunately, power rule will apply for every real number n except for n equals negative 1. As we saw in example 1D though, if n is negative 1, we can write that as 1 over x, right? And if you take, and this is what I talked about, if you take integral of 1 over x dx, that comes out to be natural log of absolute value of x plus c for x is greater than 0. And I like that. So if you can, I'm going to go ahead and just pick like a white pen and then like hide this part. Put that absolute value. Do that for me, okay? And 4x is, because we usually don't restrict that. What we usually do is we just simply say, these little things bother me, x is not equal to 0. Okay, because we want to have, the domain, well, just a different domain, really. So the most general antiderivative of 1 over x is going to be natural log of absolute value of x, not just natural log of x. So if you're typing in this on your homework and they're saying, oh no, you missed it, it's not correct, then just consider putting absolute value around your x, okay? So, all right, that was actually the third rule called logarithmic natural logarithm rule, that if n is, now this is the case where n equals negative 1. If n is not negative 1, use the power rule. But if the exponent is negative 1, if you have x in the bottom of that fraction, that's 1 over x, then you must remember that the antiderivative is natural log of absolute value of x plus c. And the next part, I guess you can keep that in your notes. If you're restricting the domain to be strictly greater than 0, then you can get rid of the absolute value signs. But very often you'll see the left expression, the left rule. All right, let's do the last rule, the exponential rule, base e. Now here's what you know. You do know that derivative of e to the ax is equal to what? A times e to the ax, right? So, we're going backward. Because we gotta get rid of this a that's getting multiplied. So you know what? Let me go ahead and just do examples of this and convince you. the rule says integral of e raised to the ax power of dx equals 1 over a times e to the ax plus the constant of integration c. And a cannot be equal to 0, as you can see, then we're going to have an undefined expression. Now, let's actually bring this guy down to our example 3, I believe. And then use this. We're going to use this and actually check the answers for A, B, and C. And we're going to be convinced that, oh, okay, this rule really works. Okay, so let's use this rule for example number 3 here. Okay, alrighty. First one. What's A in the first problem? A is 4, isn't it? Here's A is 4. So if you take the antiderivative of this expression, that's going to be 1 over what? 1 over 4 times e to the 4x power and then plus c. So just by using that, the exponential rule, I was able to find the antiderivative. But let's try to check it. Let's try to check this. What's all this? Let's try to check this. Find the derivative of 1 over 4 times e to the 4x power plus c with respect to x. What happens? The 1 over 4, we can pull this out briefly, right? So just keep that 1 over 4 there. But if you take the derivative of e to the 4x, that's going to be e to the 4x times, using the chain rule, derivative of 4x will give you what? 4, right? And plus c is just gone. That's going to be 0. So what happened with this 1/4 and 4? They will give you 1. Therefore, we get e to the 4x power. And that is exactly the same thing as the original integrand. So why do we need this random looking fraction 1 over a in front of our answer? It's because once that exponent comes down, it's gonna have to be multiplied by that reciprocal and needs to cancel out. So let's try another one. Okay, this one. What's a in this problem? A is -3, right? So if I'm just using that rule, I'm gonna have -1 over 3 times e to the -3x plus c, right? Using that rule. All right, and I'm going to check this. I'm going to see if that's true. It's a great review of taking exponential derivatives. What is the derivative of -1/3 e to the -3x power plus c? All right, that's going to be, I'm going to keep that -1/3 right there. Write down e to the -3x and multiply this by the derivative of -3x, which is -3 and plus 0. I don't have to write it, but as you can notice, -1/3 and -3, they will multiply and give you 1. So I'm just left with what? E to the -3x, and this is exactly the same thing as the original integrand. Therefore, yes, it checked. So this rule is working just fine for us now. All right, the very last one. What's a here? A is 1/2. Okay, so let's find the antiderivative. That's going to be 1 over 1/2 times e to the 1/2 times x power plus what? C. Now, I don't like to look up this first fraction. Why don't I simplify? I mean, what is 1 divided by 1/2, guys? You divide 1 by half, well, you get 2. Okay, you get 2 halves there. 2 times e to the 1/2 x plus c. And that's the answer that I'm thinking. So what I'm going to do is I'm going to check this. Check by finding the derivative of e to the 2 times e to the 1/2 times x plus c. And that's going to be 2 times e to the 1/2 times x times derivative of half x is going to be just half. And plus c will turn into plus 0. And as you can see, if you multiply this 2 by 1/2, they will turn into 1. Oh no. Therefore, I will have e to the 1/2 times x. And isn't that the integrand? Yes, that's it. So, I didn't check for every other integral problems, but I did want to check these exponential rule problems as because I didn't really explain it up here. But okay, so they all worked. Now, we're just going to do the last property, which is very similar to what we did when we were finding the derivatives. Like, remember, when you take the sum, the derivative of sum of an expression, then we can just separate them as, you know, derivative of this plus derivative of the second plus, you know. That's the rule that we're going to apply here. So, the properties of antiderivatives. First one, if you have a constant multiplier, you can pull that out to the front and just worry about that after you're done with finding the antiderivative. You can just multiply that back when you are done with it. So if you have a constant, you can pull it out. Now the second one, sum or difference of the antiderivative of sum or difference is going to be, we can separate those as sum or difference of the antiderivatives. So let's do them. Let's do example 4, and that's probably enough for the first lesson of 4.1. I'll come back and talk about the initial points in the second video. So you may not be, you're not going to be ready for the 4.1 problem just yet, because you still want to see 5, 6, and 7. But I'm still waiting for your 3.9 problems to come in. The one about how fast is, what was it? Rabat and James did an amazing job on that problem already, but I think I'm still waiting for you guys to submit it. Oh, looks like somebody submitted it already. But then the one that I'm asking is, I want you to find the rate at which shares are being purchased. I'm not asking for the share price. I'm not asking for the quantity. I'm asking for the rate at which the shares are being purchased. I'm asking you for dQdt here, okay? Q being the quantity of shares being sold or purchased, okay? So submit something. I'll take a look. If it's wrong, I'll send it back. You can fix it. You can send it back. We can do that. But start that process early for me. All right, let me go back to my 4.1 notes. Not the initial condition yet, just but this one. All right, let's find the antiderivatives, and they want you to assume x is greater than 0. And you know why they put that? They put that for b. They did. But I want to ignore that because I want to just say x cannot be equal to 0 and be okay with it. All right, let me go ahead and get my Apple Pen and try this one with you. A. So notice this is a sum of 3x to the 5th, 7x squared, and 8. I'm going to separate them. Okay, I'm going to separate this as integral of 3x to the 5th dx plus integral of 7x squared dx. And then what's the last one? Plus integral of 8 dx. Now, we did find the last one on the very first page, so we know how to deal with that. But you know what? I'm being excessive right now because I want to talk about these properties, P1 and P2, in this example. What can I do with this 3 or the 7? I can pull them out. I can pull them out to the front, so I can have 3 times integral of x to the 5th dx plus 7 times integral of x squared dx. Plus, you know what, while we are here, why don't we just go ahead and evaluate what this is? Because we know how to find the antiderivative of this. That's going to be what? 8x plus, c. 8x plus c. So that got me 8x plus c. Now we're going to go ahead and work with these two in the beginning. So 3 times, now use that power rule. Use that power rule. Increase the exponent by 1. So that's going to be x to the what power? 6 power. And divide that by what number? The new power of 6. Plus 7 times, right? 7 times. Find the antiderivative of this. Increase the exponent by what? 1. X to the what power? 3rd power. And divide that by the new power of 3. Ta-da. And then, oh dear, I'm forgetting something. Now guys, take a look. I forgot about my c over here, so why don't I add plus c there? And then I will add a plus c right there. And then bring down my 8x plus c there. All right, I'm almost done. Let me go ahead and simplify this answer a little bit. If I have 3 over 6, 3 over 6 can be simplified as what? 1/2 x to the 6 okay? 1/2 x to the 6th. What I'm doing is this. You see how there is plus c here and a plus c here and another plus c there? We're adding 3 constants together. And if you add 3 numbers together, you get another number. And that's just going to be another constant. So I'm going to just add 3c and just call it c. We don't have to call it 3c. We can call it just c. All right, so the next term that I will write is plus 7 over 3x to the 3rd power, and then plus 8x. And then I can go ahead and stick the sum of 3 c's as just another c. And that's it. Now, if you want to check this, check by finding derivative of 1/2 x to the 6th plus 7/3 x to the 3rd plus 8x plus c. And let's take the derivative real quick because we're a pro at it. 6 times half is 3, so 3x to the 5th plus 7/3 times 3 is 7, x to the square, x squared, plus 8, and plus c gives us 0. Now, is this matching what they gave us originally? And yes, it does. So check is, it's nice. It's not required, but check it. If I were you, I'll check it when I'm taking like an exam or something like that. So that's how you would do this antiderivative problem using the properties listed as you expected, right? Now, let's do the very last one. Okay, B. Now, they did say assume x is greater than 0. They needed to give me that because they really didn't need to give me that. They could have just say assume x does not equal to 0. I'm going to go with that. Yeah, I'm going to delete this. Well, if your homework problem says assume x is greater than 0, that means you can just ignore that absolute value bars around your x in a natural log. But I want to do the most general case, looking at the domain of the integrand. It just cannot be 0, but it can be a negative number. Why not, right? All right, so let me go ahead and do that. I'm just gonna go ahead and minimize this guy a little bit smaller. Alrighty, I'm ready. So, I'm going to rewrite this first, okay? I'm going to rewrite this as, I'm going to rewrite this as integral of 4 over x, okay, plus 3x over x, plus 2x to the 4th power over x. You know what I did? I just separated them into 3 pieces. All those are over x. Now, let me simplify this a little more. I can rewrite the first one is 4 times x to the negative 1st power plus 3. What happened to the x? Those are gone now. And the next one is 4x to the 4th power over x. So that's going to give me 2x to the 3rd power dx. So I just rewrite this in standard form so that I can separate them. All right, let me separate these into 3 separate integrals. Integral of 4x to the negative 1st dx plus integral of 3 dx plus integral of 2x to the 3rd dx. Alrighty. Now, that is using the second property, right? That's using P2. The antiderivative of sum is the sum of the antiderivative. That's what I just did. Now, I'm going to pull out the constants, okay? It's a little tedious, but why not? They gave me a theorem. I'm going to go ahead and use it. Oh, not that one. That's not a constant. That is just a constant. I don't need to pull that one out because I know how to deal with it. Alrighty, so let's go ahead and find it. So I'm going to get 4 times integral of x to the negative 4, oh, hello, dx, plus, now, we do know what this is. Why don't we go ahead and evaluate what this is first? This is going to give us 3x plus, don't forget your c, right? Okay, plus 2 times integral of x to the 3rd power dx. Now, this is why they say assume x is greater than 0 because they were going to give you a break. The textbook problem was going to give you a break and tell you that you can just write it as log of x, but I don't want that. I want you to write it as 4 times, what's that? That's going to be 4 times a natural log of absolute value of x. And don't forget your plus c. Plus c. And technically, these are both inside a parenthesis. Therefore, you're going to have to distribute that 4 to the c. But c or 4c, they're just unknown constants. So it really doesn't matter. You do not have to make 4c. You can just write it as a c. But let me keep going. Plus 3x plus c. And then the last one, we have to apply the power rule over here for the last one, right? That's going to be plus 2 times, my highlighter's not clicking. Oh no, my functions are all dead. I don't know what's going on. Let's see. Okay, I just have to go on now. X to the what power? X to the 4th power, because I went up by 1, divided by the new power of 4. And don't forget to put plus c, right? Let me go ahead and close this app and come back in, because I couldn't zoom out. Guys, I cannot zoom out here. I'm gonna do something a little scary. I'm gonna close that app. I closed it. All right, let's see if I can reopen it and restart it. Oh, thank goodness. Okay, that scared me for a second. So that's gonna be, I wanted a little more room. You know why? Because I wanted to add plus c after this. Plus c. Okay, so what's that going to be? I'm gonna have 4 natural log of absolute value of x. And you don't have to. I mean, don't be upset with me, because I'm not gonna write 4c. If you really want to write 4c, that's okay, but I'm just gonna write c. Plus 3x plus c. Plus, now take a look. If you combine or simplify this 2 over 4, you're going to get what? 1/2 x to the 4th plus c, right? Now, these constants, they just keep on following you everywhere. But now we can combine these c's as just a single plus c, but let's write our final answer then. Here's the final answer. 4 natural log of absolute value of x plus 3x plus 1/2 x to the 4th power plus some constant c. Now, if you take the derivative, I'm out of room, and I don't think I want to do that right now. If you take the derivative of this expression, you will get something equivalent of what used to be the integrand over there. So, last one was pretty fun, but I guess the important thing for you to remember is that don't forget to put that constant of integration plus c in your answers. And, you know, I think we can talk more about the domain and why the integral of 1 over x is natural log of absolute value of x instead of just natural log of x. But that's a great thing to talk about in another short video. I'm going to stop now. So from what I just did with you, you should be able to do more than half of 4.1 homework, just finding the antiderivatives. But then stop when you see these initial condition problems. We're basically plugging in the numbers given to find what that c is.